Hello, this is Daryl Korn, and I'm going to walk through my exam one answers. So I'm going to start with going over the first couple questions before I dive into my code for question four, and then I'll explain my answers for question four. That makes the most sense in my mind. Okay, so let's get right to it. For question one, I thought models A and C were trained fairly well. It doesn't seem like the model is overfitting for the training data, so I think they did quite well. Model B, on the other hand, was not trained properly. You can see this because the validation accuracy diverges so much from the training accuracy. So clearly it's starting to memorize the training data and performing worse and worse on the validation data. Okay, two methods to help correct this. One, we could use some data augmentation to help prevent the model from memorizing the training data as much. So we can add dropout layers or some regularization, and that'll prevent the model from memorizing its data so much. Another method would be just add some early stopping. This can either be manual or you can code in some logic to do it. If you stopped this model around, Epic 8 or 10, then it would probably generalize much better. Okay, on to question two. So question two asked to identify the filter size and the number of filters at each CNN layer for the following output model or the following model summary. So we can assume that this model had an input image of about 150 by 150 pixels. So with a filter size, with that input image, then a filter size of 7 by 7 would return this particular output image dimension of 144 by 144, because with the 7 by 7 kernel, we would lose 3 pixels on each side, all four sides of the image. So in total, we would lose, 6 pixels, which gives us 144 by 144. Similarly, 16, that's the number of filters right there. So onto our second CNN layer. We can see our input image was 72 by 72, and our output is 68 by 68. Therefore, we must have had a kernel of about 5 by 5. And our number of filters is listed here as 32. Our next CNN layer, we had a 34 by 34 image, but then we got a 32 by 32 image. So that is a filter size of 3 by 3 because we lost 2 pixels on each side. And we have the number of filters at 64. And for our last CNN layer, we had an image of 16 by 16, but then we ended up with 14 by 14. So again, we lost 2 pixels on each side, so we must have had a kernel of 3 by 3 with 64 filters here. And to answer question B real quick, like I said, if we had a filter size of 7 by 7, then we must have had and then we had an output shape of 144 by 144. Our input image must have been 150 by 150 pixels. And here is the Python code that would generate such a model summary. Okay, on to question three. So, question three, the equation for an LSTM layer is 4 times the input shape plus 1 for, some bias. And then we multiply that by the output shape plus the output shape squared. So to walk through, how that works, for our very first layer here from what we're given, the equation would be 4 times, oh, don't do that, 6, because 6 is our input shape. We're inputting, a 6 sequence, plus 1, multiply by 4, because that is our output shape, and then 4 squared, which gives us 176 parameters. Similarly, we've got 4 times 4, which our input shape is listed right here, plus 1 times 2 is our output shape, which is listed right here, times 2 squared gives us 56 parameters. And now for the dense layers, a dense layer equation is a bit simpler, where it's just output shape multiplied by the input shape plus the output shape. So we have 4 as our output shape listed right here, multiplied by 2, our input shape listed there, plus 4 gives us 12 parameters. And similarly, we have 3 as our input shape. This is our final dense layer. Multiplied by 4, our input, plus 3 gives us 15 parameters for our final layer. Okay. Here is a depiction of the architecture that I drew. We can see that we have an input layer of 6 to begin with, our sequence length of 6 to begin. Each of those are going to go to their individual LSTM cell, um, which are connected to subsequent LSTM cells as well as to the next layer of LSTM here, and they're all going to feed forward to their own to subsequent cells, but also to the next layer. But then we're going to pass to our dense layer here. And now we're not passing anymore to subsequent cells before it goes to our second dense layer and eventually to our prediction. And you can see that the subsequent predictions, because of these feed forwards down here, they would be based on previous sequence numbers. And I didn't draw like the nodes and the features that would comprise these individual cells just because they'd be really tiny. But, for the first LSTM layer, um, four, we would have 4 features in there before we'd have 2 in the second LSTM layer, and so on and so forth for the dense layers. But I didn't draw them because they would be tiny. Okay. On to question 4. So I guess we're going to take a break from the PowerPoint and we're going to go look at some code. Okay. So I'm starting with dense, my dense model. To begin with, we bring in some Python packages, and then here I use the code that was supplied, and I reshaped the data just a little bit. For dense layers, it had to be reshaped to 28 by 28 to get 784. And I also normalized the data to help improve the outputs a little bit. And then I also one-hot encoded the labels, the label columns. Label data? The labels. Before here, I compile my first dense model with low parameter count, and then I compile my second dense model with about 4 times as many parameters. Before I define some early stopping, then I fit my model and evaluate my model. Then lastly, I display, the training validation loss and the accuracy. And then I output some of the failures just to see how the model's doing and what the data looks like. And then I save my model here. The convolution model doesn't look a whole lot different, so we'll breeze through this a bit more. One thing is I do a little bit less reshaping of the data because the data, its format could already be passed into a CNN layer. So all I do is normalize the data a bit and then one-hot encode the labels. And here I compile my smaller parameter model. Here's my larger parameter model, about 4 times as many parameters. Early stopping, fit that model, evaluate that model, and then display some metrics before we see how it did. And then the RNN is similar to the CNN. Same amount of, the data could already be passed to an RNN layer, so I just normalize it, one-hot encode, compile some models, fit some models, evaluating some models, looking at metrics, looking at outputs, and saving it. Okay, lastly, I wrote a quick script to compare the CNN and RNN and dense models because I'm a graduate student and I had some extra questions. So similarly, we just, we reshape it for the dense and then we normalize it. And then we also one-hot encode the labels. And then We make some predictions here. We pull in our saved models and then predict before we here's some code that predicts everything and then finds late it finds images that the CNN got correct, but the other ones didn't. Similarly, this one is pulling out images where the RNN got it correct, but the other two got them incorrect. Okay, that's all the code. That's all there is. So, how did they do? Well, the dense model, my first model had this many parameters and got about 34% test accuracy. Model 2, about 4 times as many parameters, and achieved a bit better test accuracy at about 48%. The CNN model did quite poorly with 24% accuracy, and Model 2 with 4 times as many parameters did a little worse at about 23% accuracy. I'll go into that a bit more later. RNN, I used LSTM layers for this. Achieved about 49% test accuracy, but when I added, but with the model with many, many more parameters, at least 4 times as many, um, actually overfit a bit too much and had about only 37% test accuracy. So let's compare these things. My best performing model was the RNN model with the a fewer amount of parameters. Fewer parameters. And that achieved about 49% test accuracy. And surprisingly, the CNN model did the worst, which is surprising because, those are meant for image classification. And in general, all of my models performed pretty poorly, in my opinion. But I think this is due to I did a minimal, if any, data augmentation. I used some dropout layers. I used some L2 regularization, but I didn't do that technique of like flipping the images and rescaling them and moving them around and such. I could figure out how to do that for the CNN model, but I couldn't figure out how to pass the shape of that data to the dense and the RNN model. And I wanted all of my models to kind of be like on equal footing. And so clearly that data augmentation technique really helps boost the CNN model. And it ended up doing quite poorly without it, it seems. Uh, Apart from that, the fashion MNIST data is also quite small. They're only 28 by 28 pixels. And so for the convolution network in particular, you can't add too many layers before your image is collapsed down to like nothing. So you have to be very careful, and you can't put too many layers like that in, um, because after all the convolution layers and the max pooling, you could easily be left with just a 1 pixel by 1 pixel image, which definitely happened to me at one point. So I think that has something to do with it. You can't lose a whole lot of data in this. Um, and also, I think really it's just a tough data set. Here's an example of some images, figure 10.2, that show images that the dense network got wrong. And honestly, I can kind of see why it got it wrong. Like, it's hard to tell the difference because from like a shirt or a pullover or a dress. And similarly, like it's hard to see the difference between a sandal and a boot and a shoe. Like I personally would not score very well. And so really, 50% accuracy on this data set with 10 different classes is not terrible, I suppose. I understand where it's coming from. Okay. I think those are just all reasons why these models may not perform as well. Some more time, maybe we could find out how to improve the accuracies. Okay. And I'll quickly just compare some of my data here for the graduate extra question. These are some images that the CNN got correct, but everything else got wrong. The CNN seemed to do better with like shirts, dresses, and coats, like those sort of classes. And I think it did better with these because these images kind of had a more distinct silhouette. And so maybe you could pick up on the shape of the image a little bit better. And then images the RNN got correct are here's some example images here, figure 11.2. Um, it seemed to do better with other classes like bags and boots, stuff that may have looked a little bit more similar, and that the CNN just like couldn't quite pick up on. So yeah, that's my exam one. Thanks for listening, and we'll call it there. Thank you.